Hello, everyone. Happy Sunday. Welcome to yet again another Sunday tutoring session with myself. We're going to talk about a bunch of things today, Lewis structures. Just waiting on a few more people to join in. I know that we're starting in a couple minutes. I just wanted to see how you guys are doing. How's your Sunday going? Do you guys have some exams coming up, some quizzes? Did you do anything fun this weekend? Leave in the chat. Let me know how you guys are doing. I'm so happy that you're here just to spend time with me doing some chemistry. So I also wanted to mention as to why I'm even doing this and kind of for you to get to know who I am as a person. So I was a chemistry, just studying, Chris. Yeah, I get that. I was a chemistry major in college, and I went through a lot of the same classes that, some of you guys might be seeing if you're in college doing chemistry or science majors. So I myself struggled with chemistry, and I wish I had a tutor just to help me out, a guidance, anything really just to help me know what in the world to do. So that's kind of something that I wanted to give back to students and pretty much be someone who I know I needed in college. Or just in life in general. So this is my way of helping as many people as possible from something that I learned. So chemistry is just something that I've definitely have grown to love. In the beginning, I did not like it at all. I would say it was very challenging, and there were moments that I felt like I couldn't do it. Shockingly enough, right? I'm teaching it now. But definitely, if you just keep going with it, keep practicing over and over, you will understand it. All right. I also wanted to mention other things as to another reason why I'm doing this. So typically you guys may know that I am a tutor. That is my profession. And I typically charge $40 to $60 an hour for tutoring. However, as a thank you, because you are a subscriber, I am doing this completely for free every Sunday just to say thank you for watching, for being a subscriber, for just joining this chemistry community. So another thing that I am going to be doing, oh yeah, Ashley says, oh yeah, like that. So another thing that I'm doing is if you guys help me out to get to 10,000 subscribers, I will be doing an 8-hour, yes, 8-hour live tutoring session before your finals to help you deal with the chaos as to what finals weeks really are. Trust me, I remember. I even live it as a tutor, understanding how chaotic finals can be. So once again, if you help me get to 10,000 subscribers by sharing this to your classmates, to your teachers, to really anybody you think will benefit from these videos, I will be doing an 8-hour live tutoring session. Okay, that being said, why don't we jump into today's lesson on Lewis structures? Very, very important topic today. This will be something that you for sure have to know later on, even moving on to chemistry, or let's say if you want to be anything in the medical profession. After this class, actually after chemistry, the second half of chemistry, you will be doing organic chemistry, which does have a lot to do with structures overall. Okay, so Lewis structures overall are talking about valence electrons and the sharing of electrons as a whole. So as you see on the screen, these are the valence electrons that you do have to know. All right, so it's not based on the charges. Valence electrons are really just the electrons that are on the outermost shell of your element or your atom as a whole. So let's say for helium, or what's in the first column, everything has just one valence electron. Then we'll continue on, and then the second group. The second group will have two, and then we're going to skip the transition metals because we don't necessarily always know what their valence electrons are. Another thing is a lot of times Lewis structures tend to be just covalent compounds. Remember, covalent compounds are two nonmetals that are sharing electrons. So that's why we typically don't use too many transitional metals. And then moving on, our third group being 3 valence electrons, and it keeps going 4, 5, 6, 7, and lastly, your noble gases are 8. All right, so keep that in mind. Definitely know those valence electrons if you want to take a screenshot. That's something that I really, really recommend just locking that down. All right. So let's say if you just wanted to write down the proper notation for valence electrons just for one element. So let's start off with carbon. What you would look at first is how many valence electrons does carbon have? And carbon is right here in that fourth group. So we would see that carbon has 4 valence electrons. And how I'm going to draw it, it's not going to be like that. Instead, I want you to think of electrons that they repel against each other, so they don't want to be near each other. Kind of think of it as they're very antisocial. They're loners of the group. Now, our electrons will be, I'm going to draw it this way. There's only 1, 2, 3, and 4. So they're not going to be pairing up together just yet. All right, so that's what it typically looks like. I'm going to do another one, something like nitrogen. And I'm going to go back to my table and see that nitrogen is in the 5th group, and there are 5 valence electrons. So drawing this, I'm going to start off with just drawing one at a time. So 1, 2, 3, 4, and then coming back together, there's 5. So I didn't start off with drawing nitrogen as 1, 2, 3, 4, and 5. All right. So the difference here is really just the fact that it's only one element. There's no sharing of electrons. This is not a compound. It's just one atom or one element. So if you're asked to draw just one element's valence electrons, this is what it would look like. Not like this. This is the proper type. Okay. Now I'm going to go on to the main thing where it is going to be Lewis structures where they're actually sharing electrons. And I'll show you how that's done. So let's say we had HCl and we wanted to share these electrons. Hydrogen is in your first group, so it's only going to have 1 valence electron, which I'll place there. However, Cl or chlorine is a type of halogen, and that has 7 valence electrons. So how I'm going to draw this, it's going to be 1, 2, 3, 4, coming back around, 5, 6, and I'm going to put that here, 7. Okay. So now if I wanted to join these elements together to form HCl or a compound, then I would have these electrons share. Ashley just asked, how do you know how many electrons they have? So going back to your periodic table, it depends on the group that they're in. So all my arrows and then all those numbers, that's something that you for sure have to know. So Ashley, if you want to take a screenshot, anyone that's just joining us, if you want to take a screenshot of this, just knowing those valence electrons that I placed above every single row, so all these little arrows, definitely know that. Whatever group they're in, that's the specific valence electron. Cool. So that's where I'm getting these numbers from. So I said that hydrogen has only 1 valence electron because it's in our first group. And then now chlorine is in our 7th group, and that's going to have 7 valence electrons. So all halogens, this is our halogens, by the way, are always going to have 7 valence electrons. All right, so let's come back around. So I mentioned that we're now sharing these electrons. And once we start to share these electrons, notice that there's 1 electron for hydrogen and there's 1 electron for chlorine. As those two come together, they're going to form a bond. So 2 electrons form a single bond. All right. So I'm going to say it again. So I'm going to say, and if you guys want to jot this down, if you're taking notes, 2 electrons form 1 single bond. And I'm going to say single bond because later on, we're going to get to bonds that are like double or triple. Triple is the highest that you can go up to, but we'll get to that. So continuing on, 2 electrons, we said, form 1 single bond. And I'm still going to draw those lone pairs. These are actually known as lone pairs, by the way. 2 electrons that are together, they're a pair, they're lone pairs. So I'm going to still leave that on your chlorine. And this is the proper Lewis structure. All right. How are we doing? This making sense? Any questions? Can I clarify anything for you guys? Let me know in the chat. Or also you could ask a question. That's right down. I don't know if you guys can see that. There's a button that says ask a question. So at any point during my presentation, if you guys feel that you have a specific question, leave it there and I'll answer it at the end. Cool. And Ashley says easy. Love it. Love it. Love to hear that. All right. Chris says thumbs up. Happy face. All right. Happy about that. Moving on. Let's get into a specific rule, and it's known as the Octet Rule. So the Octet Rule, I want you to just think of 8 valence electrons, okay? So the Octet Rule is basically saying this, that now that we have, like, let's say if we have CH4, now that we have multiple elements being bonded together or sharing electrons, your central atom wants to have 8 valence electrons. So Octet Rule, oct, right? That typically means 8. All right, so I'll show you this. And what I always want to start off with is just counting up how many valence electrons there are in total of your compound. So in our case, we only have 1 carbon. Carbon's electrons, valence electrons specifically, are 4. And then hydrogen, there are 4 hydrogen. So I'm going to do 4 times only 1 valence electron that hydrogen typically has. So that would have been 4. And now I'm going to add these two together. So in total, this Lewis structure will have 8 valence electrons, or 8 electrons. All right. So the reason why I do this every single time is just to help you guys figure out how many electrons will go where, so you don't miss anything. We will have other structures that are a little bit more complicated, so it is important to really know how many electrons in total your structure should always have. So another rule of thumb is carbon is typically your central atom. So that's really a rule of thumb where carbon will always be your central atom most of the time, and hydrogen will never be. So I repeat, hydrogen will never be your central atom. The reason is because hydrogen only has 1 valence electron. So that means it could only bond with 1 other element. So in our case, however, carbon has 4 valence electrons, meaning it can create 4 separate bonds, or it can bond with 4 other elements, and so on. So what I'm going to do is I'm going to just put hydrogen all around that central atom of carbon. And what you can start off with doing, since we're just getting a feel for this, is putting your electrons for every single element. So we know for hydrogen, there's only 1 valence electron for each hydrogen. However, carbon has 4. So I'm going to place that like here. So there's 1, there's 2, there's 3, and there's 4. And all that 2 electrons are going to form a single bond. So all throughout, we have single bonds being formed. So your actual Lewis structure would look like this. Just placing those single bonds with your hydrogen. Okay, we're going to do a few more, and I will mention, typically what I do is I kind of just instantly go into drawing single bonds, because that's at least the thing that they all can have. Since we're sharing or building these structures, they're all going to at least have single bonds. Okay, so instead of just drawing all of the electrons, I actually would have started with the central atom of carbon, and knowing that somehow, some way, it has to be bonded to 4 different hydrogen. And I would know that 1, 2, 3, 4, that's going to have 4 bonds and hydrogens all throughout. Okay, I'm going to keep going with that concept. I'll still show you how everything is being shared, however. So now let's keep going with that concept. Let's say we have this new Lewis structure that we're trying to build. So first step, calculate how many valence electrons you have in total in your compound. So for sulfur, if we were to look back at that periodic table that I mentioned before, sulfur has 6 valence electrons. Hydrogen typically only has 1. However, there are 2 hydrogens, so that would have been 2 times 1, giving us 2. Adding these 2 up, we'll get 8 electrons again. Okay, so now hydrogen, we said, will never be your central atom. So our central atom has to be the sulfur. So how I'm going to align this is I'm going to put the central atom of sulfur and hydrogen just surrounding that central atom. Next, what we could do is we can then go back to that concept of putting how many valence electrons for every single element. And we said that hydrogen only has 1 and sulfur has 6. So we can keep going with this concept and say 1, 2, 3, 4, 5, and 6. And then building from here, those 2 electrons that are being shared will then form a single bond. So we'll have sulfur, 1 bond, 1 bond. And that's what I meant by, I could have just, I'm going to start over. So I could have just instantly started off with placing sulfur in the middle and then bonding that to one hydrogen because it has to bond with the hydrogen and it has to bond with a second hydrogen. So I know, okay, another single bond. You don't have to do every single lone pair as I was showing before in this demonstration. Instead, you can just start off with putting a single bond with whatever element we're going to be bonding to. Okay, let me know if that makes sense or if you want me to clarify that in the chat. So continuing on with this the structure, next, since we see that there are 2 electrons per every bond, that means that you're missing, here you actually have 4. So there's 2 electrons here, 2 electrons here. We're missing 4 more since we want 8 electrons. So I would place lone pairs on the central atom. These are your lone pairs on your central atom. So in our case, I would just put 1, 2, 3, and 4, and we can just double check by counting. So we can see that there would have been 2, 4, 6, and 8. Those are 8 electrons. We said there was 8 electrons initially. Yep, it checks out. Let's keep going. So today is really a bunch of practice of Lewis structures to really get this down. All right, let's keep going. Now, first up again, figure out how many valence electrons we have in total. So with phosphorus will have 5 electrons, valence electrons. Chlorine will have 3 times, so there are 3 chlorine, times how many valence electrons for chlorine, which is 7. So multiplying those two, we'll get 21. Now we'll add these two together, and you get 26 electrons. All right. So we're not going to place chlorine in the center because since there are 3 or multiple of them, then we know that the central atom has to just be one central atom. We can't have multiple for the specific case. So I'm going to put phosphorus in the center, surrounded by chlorine. And there's 3 chlorine. And now I'm going to go back to just that method that I was talking about where we're just going to put single bonds to everything. So since phosphorus has to bond to 3 other chlorine, I'm going to place a single bond between them because that's at least the lowest thing that it can definitely be. So let's count and double check. Do we have 26 electrons? We really don't. So, and I saw that by seeing this first bond in here. Let me help you count. So one bond we said was 2 electrons. So this was 2 electrons, 4, 6. We have 6 electrons. Now, continuing on, we said that chlorine has a total of 7. Each chlorine has 7 valence electrons. So we have to place lone pairs all throughout chlorine. How I'm going to do this is a little bit different than what I was mentioning in the very, very beginning, where if we were to just have chlorine as a whole, you would place chlorine as 1, 2, 3, 4, 5, 6, and 7 coming all around, right? So with these types of halogens, you actually can you can do that again. I just want to mention that it's either way, they're all going to be surrounded. And let me show you. Either way, they're all going to be surrounding that chlorine and there'll be 1 electron there. That's always the case. However, if that didn't make sense, I can go back and just go with the initial method that I was mentioning. So continuing on with that method, chlorine we said has 7 valence electrons. So I want you to think of this as chlorine has 7. So I'm going to focus on this chlorine right now. And there's already 1 here. I'm going to keep going. So 1, 2, 3, 4, 5, 6, and 7. I'm going to do that same thing for all the chlorine surrounding. So this would have been 1, 2, 3, 4, 5, 6, and 7. Keep going. 1, 2, 3, 4, 5, 6, and 7. All right, so let's count and see if we have enough. So from our bonds here, there are 2 electrons per every bond. I'm going to do a little bit of math. So since there are 2 electrons per every bond and we have 3 bonds, that means there are 6 electrons for our bonds. Next, we said that each chlorine possesses 7 electrons. So 7 times each chlorine, there are 3 chlorine. Multiplying those two. And I realize, I think I counted too many. I did. We would have had 6 electrons and Let me make sure I did that right. Phosphorus we said has 5, and then chlorine had 7, 21. Yes. Another way to look at this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There we go. I prefer doing it that way. So 24 electrons so far we want 26 electrons. So we don't have enough. We only have 24. So I'm going to place a lone pair on my central atom. So lone pair, that right there gives us 26. Making sense? Let me know. Let's do another type. Ashley's golden. She's happy. She's getting it. Love it. So let's count up. Let's count everything again. How many valence electrons do we have? Nitrogen has 5. Hydrogen typically has 1. However, there are 3 hydrogen. So 3 times the 1, that will give us 3. Add these 2 together, we get 8. All right, so now nitrogen will be our central atom. Now I'm going to place the hydrogen surrounding it. Okay, and by the way, it doesn't matter where you put this hydrogen. It can be on the bottom, it can be on top. For Lewis structures, that doesn't necessarily matter as long as your electron count is correct and the bonding is correct. So continuing on with this, now I'm going to place a single bond to every single hydrogen. So we just created 1, 2, and 3 bonds. 3 times the 2 electrons that it possesses, then it's 6 so far. However, we need 8. So I'm going to place lone pairs, 1 lone pair on your central atom. So right then and there, this is 2, 4, 6, and 8. And once again, keep going with that octet rule. This is really telling you that, yes, there are 8 valence electrons on your central atom, which is nitrogen. And I realize I'm going to go back real quick, just really overemphasizing that octet rule. So we lock that in. So our octet rule, we said that there has to be 8 valence electrons surrounding your central atom. Looking at this, phosphorus is our central atom. So I'm going to count. And this is 2, 4, 6, and 8. Yep, phosphorus is happy. So it follows that octet rule. And then same thing goes for sulfur. In this case, we saw that this would have been 2, 4, 6, and 8. Yep, checks out, follows the octet rule. It also follows how many valence electrons we initially said there were. That's the octet rule. Ashley says this is so helpful. Oh, so happy to hear. So happy to hear. I will be showing you guys all of my little tricks, everything that I've just seen in the past, 10 years of teaching and just chemistry in general that I've seen. I see a lot of these on exams, on extra credit questions, on mastering chemistry, sapling, you name it. So I'm going over a lot of this. Now, the next thing is going to be your exceptions to that octet rule. And I placed that. I made it very nice for you guys. I recommend at the moment, take a screenshot. Really, this is so helpful. These are all of your octet exceptions. So in the purple, you'll see that that's going to be the incomplete exceptions, meaning it could have anything less than 8 valence electrons on your central atom. And then the expanded octet exception just means that it's going to have more than 8 electrons. So we're going to go over this. I just mentioned if you have to take a screenshot, I really recommend doing that now. Okay. Continuing on with this, so I'm going to mention, I'm going to go over the incomplete octet rule, and I mentioned that that was specifically when you have less than 8 valence electrons on your central atom. So this is where you will actually see that being the case on your periodic table. So right here, carbon is at 4, and anything above 4 or more valence electrons, you will have a complete octet. Now, anything below, which is all of this, everything in purple that I'm mentioning, that 3, that 2, that 1, everything there will have an incomplete octet, meaning our central atom will not have 8 valence electrons, but it's okay to have less than 8 for that specific type. For example, the ones that I always see is going to be boron or beryllium. Those are really, really common cases. and we'll do some. So let's start with this first one with boron and then attached to chlorine 3, starting off with just our valence electrons. So going back, boron only has 3 valence electrons. So right then and there, we know it has to be an incomplete octet if your central atom has less than 4 valence electrons. So in our case, we only have 3 valence electrons for boron. Then chlorine, there are 3 chlorine times 7, because there are 7 valence electrons for chlorine. That would give us 21. Add these two together and we get 24 electrons. We said that boron was our central atom. So I'm going to place that. Boron is our central atom surrounded by 3 chlorine. And then I'm going to just attach single bonds because they have to bond to each other either way. So attaching a single bond here, this gives us 2, 4, and 6. So we have 6 valence electrons. We need to now get to that 24. Where we're going to end up getting to 24 is just by adding those lone pairs all around chlorine. So in our case, we'll see that I'm going to go back to that topic again, and this would have been 1, 2, 3, 4, 5, 6, and 7, because chlorine has 7 valence electrons. I'm going to do that all throughout. So then here again, 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. And if we were to recount all of this, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 valence electrons overall. Yes, it checks out. However, boron is an incomplete octet because there's only 2, 4, and 6 valence electrons on your central atom, which violates the octet rule, but it's okay because it is an exception. Let's do another type, another common one. Another common one would be beryllium. So let's figure out beryllium's valence electrons and fluorines as well. So going back to that periodic table, beryllium is right here. So right here, right? So that's going to give us 2 valence electrons. So right then and there, boom, yep, incomplete octet. This gives us 2 valence electrons, and fluorine, in this case, will be 2 times how many fluorine would have, and that would have been 7. So 14 plus 2, giving us 16 electrons. Beryllium is our central atom. So let's draw that out. So looking at this, beryllium will be our central atom surrounded by 2 fluorine. And then just placing those single bonds in between those elements, since they have to bond either way. And then from there, I'm going to count. And I'm going to keep going with this. So this would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 15, and 16. Yep, it checks out. There is only 2, 4 valence electrons around that central atom. It is an incomplete octet. Let's go to the other exception where it's an expanded octet. So your expanded octet, meaning it can have more than 8 valence electrons on that central atom, is going to be everything that is in the third row, right? So this is the third row, right then and there, that will be your exceptions to the octet rule, meaning it can be an expanded octet rule. So we'll see it's everything from 3 and sometimes they say it in like the books or in class, 3 and above. I get what they're trying to say with that. They're trying to say that it would have been like 4, 5, 6, and so on. I always think of it as kind of the opposite, because row 3 and like below, like visually, that's how I see it. So that's typically what I mention. So I typically say it's row 3 and below, just because how you see it on the periodic table. But really what they mean is you're increasing your row numbers. That's why they say 3 and above. But really just knowing this box here, that red box, that will definitely be on exams, just hinted to let you know. So continuing on, our expanded octet, which we mentioned was more than 8 valence electrons. This is a common example. Right then and there, we see that sulfur for sure has to be our central atom, since it is going to be surrounded by 6 fluorine. So I'll still count how many valence electrons we're going to have. So sulfur will be 6 valence electrons. And then fluorine has 6 different fluorine times 7, which would give us 42. add those two together, and that gives us 48. And then we'll place sulfur as our central atom. So doing that, sulfur is our central atom. I'm going to put the fluorine all around. So our fluorine all around, we said we were going to have, goodness, we're going to have 6. All right, so 1, 2, 3, 4, 5, and 6. Yep, that's right. And then now continuing on, I'm going to add bonds to everything since it has to bond all together. So this would have been 1, so 2, 4, 6, 8, 10, and 12 so far. Okay, I'm going to keep going now. So we have 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Whew, yes, 48 valence electrons altogether. It's allowed to have more than 8 valence electrons on your central atom of sulfur. And we can see that here by counting 2, 4, 6, 8, 10, and 12, as we mentioned. So that actually has 12 valence electrons altogether. That's allowed since it is one of your exceptions. All right, so I do want to move on. I want to get back to something else that you will definitely see. Let's get into more of these complicated structures, and something that is actually going to be helpful to figure out what different type of structure it is going to be something known as formal charges. So formal charges, all I really want you to think of is a formal charge essentially is the charge of that element within that compound. So within that Lewis structure, a lot of times there can be a formal charge of something other than its valence electron. And it'll make more sense once we do it. So let's look at this. Let's look at carbon monoxide and focus on the valence electrons all together. So carbon, we said, has 4, oxygen has 6, adding those together, and we get 10. So total of 10 electrons. All right. So this one doesn't seem to be too tricky so far, right? Yeah, it'll get there. It'll get there, but it's not too bad. So continuing on with this concept, I'm going to place just carbon and oxygen right next to each other because there really is no central atom. Sometimes you actually might have 2 central atoms since really there's only 2 elements being bonded. Now I'm going to continue with this concept, and I'm going to just start off with putting a single bond. Right then and there, we only have 2 electrons. We want to make 10. So I'm going to say, all right, we have 2, 3, 4, 5, 6, 7, 8, and 9, and I'm going to say 10. Okay. Now, I know I drew this differently, right? You're probably used to seeing just this all around. Just have one element. This is the proper setup for carbon or a Lewis structure. That's really just showing the valence electrons. For our actual real Lewis structures, you are allowed to have those lone pairs together. Okay, so I know that this is completely different. This is just really how it's written, but just knowing that carbon, since it's by itself and there is no sharing of electrons, this is how we properly write the valence electrons. However, now we're getting into more complicated structures and we will be just instantly pairing those electrons together. All right, so continuing with this concept, carbon is not happy. Why? Because it doesn't complete the octet rule. So carbon will always complete the octet rule. However, here it does not. So this is not the right structure. So what we're going to do instead is we're going to donate electrons to build a stronger bond or a higher bond. So I'm going to donate these electrons, these lone pairs from oxygen to form a double bond. So I'm going to form a double bond. And now these went away. So we only have 2 lone pairs on oxygen and we still have 1 lone pair on carbon. So let's count again and see, is carbon happy? So we see there's 2, 4, and 6. Nope, still not happy. All right, so we're going to keep donating. So oxygen is going to donate another lone pair to make carbon happy to complete that octet rule of 8 valence electrons on carbon. And then we'll see, okay, now we have a triple bond, which is very strong. And we'll count again. And we see that, okay, we have 1, 2, 3, 4, 5, and 6, and 7, and 8. Yes, carbon is happy. So is the oxygen. Oxygen also is going to be our central atom in this case, where that will complete that octet rule. So this checks out. Okay, that's definitely something to note. Another thing I wanted to get into, just a little note, little trick for you guys, is whenever we were to have, let's say if we're bonding to some sort of central atom, and you only have a single bond, and let's say you just have oxygen or some sort of halogen, it can be chlorine, fluorine, so on. And what that's going to look like is we're always going to have just 3 lone pairs whenever there is a single bond. Now, if we were to have a double bond, you will only have 2 lone pairs. If you were to have a triple bond, there's only 1 lone pair. Okay, so get used to seeing that setup. That's always going to be the case, specifically with these types of compounds. All right. So let's go back and let's practice doing, here, let me actually get into the next one. The next one's really good. Let's practice doing some formal charges, come to think of it. All right, so this is a specific formula for formal charges, and I'm going to draw out just what we said our compound was, our Lewis structure was. So we said there was a triple bond and there was 2 valence electrons on carbon and an oxygen. So for formal charges specifically, let's start off with carbon. So formal charge of carbon, I'm going to say FC of just carbon. We're going to start off with our valence electrons for carbon just generally. So carbon has 4 valence electrons. Now we'll see, I'm going to subtract by the bonding electrons. A lot of times they also call this as half bonding. All that really means is you're looking at your bonds and you're seeing how many electrons are just being bonded to carbon or whatever formal charge you're trying to find. So in our case, there's 1, 2, and 3. So there are 3 bonding electrons. Those electrons once again come from your bonds. And then now I'm going to add each individual lone pair on that carbon. So I know that these are lone pairs, but we're actually going to count them as 2 electrons. So I want you to think of that as plus 2. Okay. So then in this case, this would have given us 4 minus, and I'm going to actually add these 2 together. So that would have been 5 and 4. So that would have been a -1 charge. And then now I'm going to do this again. And then I'll look at oxygen. And let's see, let's erase this. Come on. So now I'm going to look at oxygen. And we'll do the same sort of setup where this would have been oxygen. That would have been 6 typically. Then I'm going to see that, yes, again, this would have been 1, 2, 3. Okay, that would have been 3. So 3 bonding electrons, and then plus however many lone pairs that we have or individual electrons. So this would have been 2. That gives us 6 minus 5, which gives us a +1 charge. And now this would have been 4 minus 5, which gives us a -1 charge. So this carbon would have been a -1 charge, and oxygen would have been a +1 charge. Now I'm going to continue with this. And now this sort of setup, going back to kind of something like this, typically we want the most electronegative atom to be negative. Okay, so in our case, here, let me go back to what even electronegativity is. You guys will, if you haven't learned electronegativity just yet, you will. So let's say I'm going to just draw a generic periodic table, and your electronegativity is going to increase as we go across the periodic table, and then also upwards. So really your most electronegative atom will be fluorine. That's what I typically always look at, is just whatever is the most electronegative. This will make sense once we kind of try some more things. By the way, electronegativity, all that is really just how much that element wants to attract other electrons. Okay, so how attractive that element is to attract other electrons. Okay, So we'll continue with this concept of formal charges and also get into some other different structures. So let's say something like resonance. In our case here, this would have been, we're going to get into resonance real quick, but I'm going to just mention this sort of structure. So it started off with just how many valence electrons we have in total, where nitrogen would have been 5, and then oxygen would have been 6 times the 3, which is 18. And then now notice that there is one negative charge here. So that negative is actually going to add on to how many electrons we have. So I'm going to say +1. So then in total, we will have 6 plus the 18, right? 18 plus that 6, giving us 24 electrons. Okay. Continuing on with this, I'm going to place that nitrogen as our central atom. And let me get some more room. Nitrogen as our central atom, surrounded by 3 oxygen. And then from there, I'm going to place a single bond for everything since they have to be bonded either way. And then we're just going to count. So what I'm going to do is I'm just going to instantly start off with placing lone pairs all around oxygen. So far we have 2, 4, 6 with those single bonds that I've added. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And okay, it seems good so far, right? No, it violates the octet rule. So nitrogen needs one more bond. What we're going to do with that now is one of the oxygen will then donates its bond to form a double bond. Now, which oxygen will do that? And that's where resonance comes in. So any of these oxygen would have been correct. Doesn't matter which oxygen would have actually donated that, that lone pair. They all would be right. So I could have done this oxygen. I could have done this oxygen. Could have also done this oxygen. All of those are possibilities. This is known as resonance. So resonance, let's go back to give you guys a definition. Resonance is whenever 2 or more Lewis structures have the same exact arrangement or structure, really. So there is no difference. They all can be, it's a possibility. That's what I want you to think of. So I'm going to go back and show you all the different types of resonance structures and show you a little trick as to figuring out how many resonance structures there typically would be. So in our case, I'm just going to start off with the first type. So this is the first type, second type, and third type. I'll start off with the first type where nitrogen would have been our central atom, and we'll have oxygen surrounding all throughout with our lone pairs. And then now this would have been a double bond and only 2 lone pairs since we donated one already. And then lastly, since this is charged, all Lewis structures that have a charge will be placed in brackets, and that would then have a negative charge. I'm going to keep going with that. So the symbol for resonance is just a double arrow, and that just symbolizes that it's resonance. And then continuing on, so this would have been our first type. Our second type is the second one here where, okay, I'm just going to put that double bond on that top oxygen, and the other ones would remain the same. So that's our other possibility. Once again, bracket, negative charge. So let's keep going with that. Now, our last type would have been the third one. So this could have also been nitrogen in the center. Everything else is single bonded. And we would then have a double bond on our oxygen here and a negative charge. That is our third type. We have 3 different possibilities of resonance structures. So these are 3 resonance structures in total. Why 3? Because there are 3 oxygen. Right then and there, I could have just spotted that as I saw it. However, it won't always be the case. I don't want you to just instantly think that. So if you see that, let's say you could have donated lone pairs from either one of those oxygen. Since there are 3, then you know, okay, there's going to be 3 resonance structures. That's a little trick right there. All right. Continuing on. Another really, really important type. So I've seen this one on a lot of exams or extra credit questions, just a very, very common example. So I would really recommend writing this one down and just knowing this. So in our case, we have something like this. First step, as always, figure out how many valence electrons in total we have. So I'm going to start off with that oxygen. And oxygen has 6, carbon has 4, and nitrogen has 5. And then lastly, we have a negative charge here that adds 1 electron. So adding this all together, we get 16 valence electrons. Now, which one is our central atom? Not sure, right? Looking at it, you maybe don't know. Carbon. Carbon is typically your central atom. Okay, so that's something that is, if you're not sure, try putting carbon in the center. And a lot of times it's actually given to you how it's written. I don't want to say every single time though. So a lot of times carbon will just be in the center. It is a very, very good central atom. So continuing with this, let's draw all the different possibilities of that OCN negative. I'm going to put carbon as our central atom and surrounded by oxygen and nitrogen. And then from there, we'll put a single bond in the center. So single bond there, right there, we see that we have 4 electrons so far. I'm going to keep going. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. That's 16 electrons, right? Yes. Okay. Is this right? For those of you who say no, it's because it doesn't follow the octet rule. Carbon will always follow your octet rule, meaning there are 8 valence electrons in your central atom. So we have to donate. So there are several different possibilities, and formal charges will tell you which one of these structures is the best. Okay. So in our case, I'm going to say, why don't we start off with donating 1 electron from each element. All right. So if oxygen were to generously donate an electron and nitrogen donates another one. If this happens, then we would then see that carbon would form a double bond with oxygen and nitrogen. So it would form a double bond with both of those elements, and we would only have 2 lone pairs on either side. Remember that this is a charged structure, so we'll put this in brackets with a negative charge. And that's just because that's what the charge was initially. Now I'm going to keep going. So we could have had that possibility, right? That's one. Now the other possibility is let's say just oxygen. So let's just say oxygen donates 2 electrons. So this donates 2 electrons to form a triple bond. So I'm going to say, all right, the other possibility, and I'm not saying it's resonance just yet because we don't know. We have to check, is it the best structure? Because they're not all the same right now. So I'm going to put carbon and I'm going to place a triple bond and just a single bond on nitrogen, placing this in brackets because it is charged. And then we'll try out another one. And the other type could have been nitrogen donating 2 electrons. So I'm going to show that. And so if nitrogen donates 2 electrons, then we'll have a triple bond on nitrogen. And a single bond still remaining on oxygen, placing this in brackets because it is a charged Lewis structure, so making that a negative. All right. So just looking at it, there isn't a way to just tell. Okay. So this is why formal charges is so important. I'm going to just start off with figuring out all of the formal charges of every single element. And then a lot of times this question is actually going to be asked as which structure is more favorable or which structure is the best out of all of these structures, okay? Or which structure is the major structure? I've heard it so many different ways. So this is definitely want to know. So I'm going to start off with this first structure. And I'm just going to look at the formal charges of oxygen. Okay. So the formal charge of oxygen would have been our valence electrons, which is 6, minus however many bonding electrons there are on oxygen. So there's 1 and 2. We see that 1 and 2. So right then and there, 2 electrons that are being bonded just to oxygen. Now I'm going to count exactly how many electrons there are on oxygen. So there are 2 and 4. Okay, I'm just counting the individual ones. I know that it's typically lone pairs. However, for this specific formal charge formula, you do count up the individual electrons. So that would have been 4. Now that makes it 6 minus 6, giving us a 0, neutral charge. So this charge right here is 0. All right, let's check carbon. So formal charge of carbon, carbon typically has 4. This would then be minus however many bonding there is to carbon. So here there is 1 and 2 and 3 and 4. So 4, plus there is no lone pairs surrounding carbon, not on your central atom, so there's 0. And then this would have just been 4 minus 4, so giving us 0 again. So our formal charge is also 0. Okay, not too bad so far. Now let's do nitrogen. So nitrogen, we'll see nitrogen typically has 5 minus our bonding. And our bonding, just for nitrogen, there's only 1 and 2. So right then and there are 2. And I'm going to add however many lone pairs we had. So each individual element, there's 2 and 4. So that would have been 5 minus 6, giving us -1. So all of these formal charges will add up to your overall charge of your compound. So in this case, that does add up to -1, but it's not the best one. And I'll tell you why. So this is going back to electronegativity. Electronegativity, as I mentioned before, increases as we move to the right and go up on the periodic table. So the one that's actually closest to fluorine, because that's our highest element here. There's fluorine, there's oxygen, and then there's nitrogen. Oxygen is more electronegative. The most electronegative atoms want to be negative. Okay, and once again, electronegativity was really just the fact that it's able to attract other electrons. So in our case, nitrogen is not the most electronegative. That's why this structure does not work. It is not favorable. So let's try another one. So since that didn't work, why don't we try the second type and see, is that one the most favorable? Will our negative charge be on our oxygen? Because that is the most favorable. Okay, so maybe, we'll see. So now looking at this, I'm just going to figure out our formal charge of that oxygen. So oxygen's valence electrons are 6 minus the bonding of just oxygen. So looking at those bonding electrons, here's 1, 2, and 3, plus there are 2 electrons. So right then and there, that's 6 minus 5, that's +1. No, that's not good. Electronegativity, the most electronegative atoms, which is oxygen in this case, doesn't want to be positive. It's negative, wants to be negative, or it wants to be 0. So in our case, this would have been a +1. Right then and there, it's not great, but I'm going to keep going and I'll show you what the other ones would have been. So carbon is typically 4 valence electrons minus the bonding, which would have been 1, 2, and 3, and 4. So 4. There are no lone pairs overall. So that would have been 0. So 4 minus 4 giving us 0. That's a 0 formal charge. I'm going to keep going. And then I'll see that nitrogen, formal charge of nitrogen, would have then been our overall valence electrons of nitrogen, which is 5 minus, let's see, there's only 1 bonding electron. So, okay, that's only 1, plus however many bonds, or lone pairs, I'm sorry, that there are. So individual elements, again, this electrons, this would have been 2, 4, and 6. So 5 minus 7, 2. That's not favorable at all. So we never want anything to be in the 2s. 3s is not good at all. Okay, so that is definitely something to check and to watch out for. You don't want a -2 or a +2 charge overall. You either want everything to be 0 if it's a neutral compound, meaning there is no charge, or if it is a charged compound, you want it to typically be +1 or -1. Okay, so continuing on, this didn't work out either. All right. So by process of elimination, we know that this next one will work, but I'll tell you why it works. So let's start off with this oxygen, doing the formal charge of oxygen. And we'll start off with our 6 valence electrons, because that's what oxygen has, minus however many bonding we see. So there's only 1, plus each individual electron. So we'll have 2, 4, and 6. Right, then in there we have 6 minus 7. That is a -1. And that -1 charge is placed on our most electronegative atom, which is happy, it's favorable. So I'm going to keep going and show you the rest. And then from there, formal charge of carbon, valence electrons is 4 again. And then in our case, we'll see that this would have been only, let's see, we have 1, 2, 3, 4 bonding electrons plus 0 electrons. There are no lone pairs on your central atom, giving you a charge of 0. So that's 0. Now I'm going to go on to nitrogen just to double check. That would have been a formal charge for nitrogen, starting off with the valence electrons of nitrogen, giving us 5 minus our bonding. So that's 1, 2, 3. And then plus however many individual electrons. So there are 2. And that's 5 minus 5, giving us 0. This is the best one because our most electronegative atom is oxygen, because whatever is closest to fluorine is your most electronegative. Electronegative atoms want to be negative, want to be the negative charge overall. And then your central atom prefers to be 0. And that's the case in this case. We would have said that this is the best structure. This is the most favorable, the major structure. Either one of those is correct. So let me know if you have any questions on what I just did. So in our case, this is not resonance. All of this chaos here, this is not resonance, okay? Because not everything is the same. In our case, we used formal charges to figure out what is the most favorable or what is the strongest structure, what is the best structure that we could possibly have. So for formal charges overall, as I mentioned, we want that that central atom to be 0 preferably. And then we want our most electronegative atom to be negative if we have to have a negative charge. And then that's kind of what we'll keep seeing each time. All right, so we can do a few more questions here. I also want to open it up to any questions that you might have. Let me know in the chat if you guys have any specific questions, if you have a specific structure that you want me to go over in these last few minutes. Definitely let me know. This is your time. I just want to really help you guys out. And then I also wanted to mention that next time I'm thinking about talking more on different geometries, so molecular geometries and really just overall shapes. They have specific names if you guys haven't gotten to that just yet. And I'm also going to touch on polarity. So that's another big topic that we will, it's all based on Lewis structures. So really practice these. I'm going to try a couple since I'm not seeing any questions so far. All right, so let's do another type. This one is CO2. And as we said before, we're going to start off with just counting how many valence electrons we have, adding that all together. So we have carbon. Carbon has 4. Oxygen, there are 2 oxygen. So 2 times 6, that would have been 12. 12 plus that 4, giving us a total of 16 electrons. Carbon is typically always your central atom. And I'm going to need a little bit more room than this, so let me scroll down. So we'll be doing CO2. We said that carbon is typically your central atom. So I'm going to place the oxygen surrounding it and a single bond, and then I'm going to just put all my lone pairs. So we have 2, 4, 6, 8, 10, 12, 14, and 16. Okay, seems fine. Doesn't complete the octet rule. So I'm going to donate some lone pairs. And we could have several different things again. This is another type where we have to double check formal charges and just really figure out what structure is the best. So I'm going to donate, let's say I were to donate from either side. That's one possibility. And then that would give you a double bond on both oxygen. So that's one possibility. And this is a neutral compound, so there's no charge. So there aren't any brackets. And I'm going to do another type. So let's say if instead just one of these donates an electron. If that were the case, this would have been a double bond with just 2 lone pairs. Now, it could have been the opposite side, and actually even then, I'm going to actually stop right here and just tell you guys, this wouldn't work. Now, this wouldn't work, and actually it would have been like this. This wouldn't work because carbon is still not happy. So in our case, carbon would have just been 2, 4, and 6, wouldn't have been 8. So I have to donate more electrons. I would have to keep going and make this into a triple bond. And right then and there, that would have completed the octet rule, and that's one possibility. I could have also done the opposite side, where this would have been the other oxygen donating, and it really looks the exact same. It just flipped over. Let's check. Let's see, does this work? So doing our formal charges again, I'm just going to do this oxygen. So I'll do oxygen 1, and you'll notice that the oxygen are actually going to be the same charges since they're both the same on either side. This is symmetrical. So in our case, we're going to start off with our valence electrons of oxygen, which is 6, and then minus, minus our bonding electrons. So 1, 2, this would have been 2. And then this would have been plus each individual electron, so 4. And this is 0. So this is 0, and this one's also 0 since it's really the same oxygen. And we'll do the same thing now for carbon. So carbon's valence electrons are 4 minus 1, 2, 3, and 4. And then plus 0 since there are no lone pairs. So that's 0. This is preferred. This is definitely something that you want to notice is that if all of your formal charges are 0 for a neutral compound, so neutral just meaning that initially there was no charge to begin with, then right then and there we know that this checks out. That works. Still want to keep showing you the other ones though. So this is definitely a case. Let's double check the others. So if I were to look at this one and see that, okay, what if I were to check this oxygen here, this first oxygen, and then we'll move on to this second oxygen. So this oxygen starts off with 6 valence electrons minus, we'll do our bonding, and this is 1, 2, and 3, plus only 2 electrons. Right there, that's 6 minus 5. That's a positive 1. That is not good at all. Why? Because our electronegative atoms do not want to be positive. They would rather be negative. So right then and there, I can stop and I can see that that is not going to be preferred. Same thing goes for this other one because it's really its mirror image, where this would have been positive. So no, these are not the correct structures. So beware of that. Whenever you aren't sure, use formal charges as your way to be sure. So in our case, formal charges can be used if everything is 0 and it's a neutral compound, then right then and there, you know that that will be correct. If your most electronegative atom is not 0 or a negative number, then it won't work. So right then and there, that rules that out. Okay. So that's it for today. Thank you so much for joining and being here on a Sunday, working together on chemistry. I really hope that this helped. Let me know specifically if you want me to do any other topics for next Sunday besides geometries or polarity. Definitely let me know in the comments. I just want to know what you guys need help with because I know everyone's on something different, but I will see you guys next Sunday. Definitely reserve your spot for next week so we can be here together again and really just acing your chemistry class. Thank you once again and have a great night. See you guys.